Hey everyone, welcome back to this course on DC to DC converters. This week we're going to be taking a look at electrical parameters. So just as a reminder of what we're doing, we're reading through this DC to DC Book of Knowledge, which is available for free on that link. And we'll be meeting Mondays from 5 to 6 p.m. Pacific time, and then the schedule is available on this link here. Just as a quick note, I have updated the schedule. This week we were supposed to talk about electrical parameters, measurement, and thermal parameters, but after looking through the chapter in the book, I decided to condense it down to just electrical parameters. So that's the schedule. And that's where we are today. Here's a knowledge check from last week. So just as a reminder, we looked at control, right? Closed loop control, gain crossover frequencies, and then looked at phase and gain margins and compensation last week. So you should take a look at these questions, try to answer them, and if you can reasonably get through them, you should be well set for a interview type situation. This are some updates to the solar panel Arduino project. So actually, I haven't worked on it too much, but I will be going through the layout today. So as a reminder, we've already done and walked through the design and schematic. After our discussion on electrical parameters today, I do want to talk about laying out the PCB, and I'll walk through some of that and document at all those results here in this link. Then last week we had a project to design a flyback converter to convert 48 volt Ethernet to 5 volt at 2 watts to power 2.5 watts to power an Arduino Mega. And I'll also be going over that design after this discussion. I actually haven't done it yet, but it's relatively straightforward and we can pretty easily go through it, I think. All right, so getting into our discussion on electrical parameters. So datasheets have a lot of these electrical parameters in common. Here I've just listed out some different parameters, that you'll see all over the place, right? So we've got our minimum input voltage, quiescent current, operating current, right? These are all kind of like input power type electrical parameters. And then we have the feedback voltage tolerance. So this is specific to any kind of feedback controller, which requires some kind of divider network to compare to an internal voltage reference. And so that voltage reference that's inside the chip will always have some kind of tolerance, and we'll look at that. Some other electrical parameters are line regulation and load regulation, right? So these describe how robust our output voltage is when we have some kind of change in the line or some kind of change in the load. And then next up, we have oscillator frequency, right? So this is typically set using some kind of timing resistor, or some chips also have a fixed oscillator frequency. But in any case, the datasheet will specify, the range of values that that oscillator will take. And so this oscillator frequency relates to the switching frequency of your, your switches in your switching regulator. And then last up, we have the on resistance. So this is specific to MOSFETs, or any kind of transistor, really. But MOSFETs specifically have what's usually called RDS on, right? The drain to source on resistance, right? So when the MOSFET is conducting, then current is flowing from the drain to the source, and that path actually has some amount of finite resistance, right? Ideally, it would be zero, but of course, there's some resistance, and that resistance will lead to copper loss or conduction loss. And then lastly, we have current limits, which are kind of related to the on resistance, right? If we have some amount of resistance, and then current is flowing through that resistance, the part will heat up, and then at a certain point, it'll just get too hot. So the data sheet will usually tell you what to limit that current passing through, your switch should be in order to keep it operational. All right. So throughout these examples, I'm just going to be going through this LT8609A datasheet. So as a reminder, this is actually the switching regulator IC that I picked out for the solar powered Arduino project. So, it's kind of convenient to just step through the datasheet itself. So if you go to this link here, you can actually see what this 30-page datasheet looks like, right? So it's usually a good idea to kind of break down the data sheet and try to understand various parts of it because it can be intimidating at first. There's a lot of information here. You don't always need to use all of it. I mean, you should always consider all of it, but when you're making a first cut of a design, you don't necessarily need to utilize everything that's in it, right? All right. So first of all, we have our minimum input voltage, and so this is the minimum voltage that's required really to power any auxiliary circuitry which is inside the chip. And sometimes, right, this actually acts as a supply voltage, and sometimes it's just straight up the input voltage, right? Some chips will have a separate VCC pin or something similar that is actually used to supply power. But this one in particular, the input voltage is actually being used to power the auxiliary circuits. Right, so you can see there's no separate VCC pin. There is this int VCC pin, which is actually an internal regulator. Right, if you read through the data sheet and you look up the int VCC pin, you can see, right, it'll usually tell you the different pin functions. And so here you can see that this is an internal 3.5 volt regulator, right? So this is actually not necessarily an input to this chip, right? So we don't really need to apply any voltage here to power up the chip, but we do need to put a capacitor here to actually hold up that 3.5 volt internal regulator there. But anyways, minimum input voltage here, in this case, we have a minimum of about 2.7. And so again, these data sheets will typically specify a range of values. In this case, they specify the typical value and the maximum value. And in this case, the typical minimum input voltage is 2.7 volts. And so we talked about the quiescent current. So this is what's actually powering the auxiliary circuitry. I think I have a screenshot here later. So, right, there's a bunch of different circuitry within the switching regulator IC, right? It's not just black box magic, right? It needs some kind of power source. And so in this case, it's coming from the quiescent current, right? We're pulling in current from that voltage, that input voltage pin in order to power all of the different circuits inside of the chip. And so this current is typically independent of the input voltage, right? So it just needs a little bit of this bias current to turn things on. And sometimes apart from the quiescent current, the data sheets will specify an operating current. And so in this case, right, they specify the current when our switching converter is in regulation, right? So when the output voltage is actually regulated and it's at some value, this is how much current is going to be pulled from that input voltage source in order to power up the different devices. Right, and you can see it's a considerable change from just the regular quiescent current. So here in this case, when our enable pin, for example, is 2 volts, then we have 1.7 microamps typically. However, when we do have a load attached, you can see that operating current, right, that's being sourced from the input voltage is now 480 microamps, right? So we've gone up by about 300 times or 400 times ish. So it's just something to keep in mind, right? This might be negligible depending on your voltage source, right? Your input voltage source, maybe it can handle um, on the order of microamps more current, but maybe it can't, right? It's just something to keep in mind, right? You need to know what this voltage source, this input voltage source is capable of before you start using all of these ICs. All right. And so next up, the feedback reference voltage. So these will always have some amount of tolerance as well. Um, and as a reminder, what this feedback reference voltage is doing is it's serving as a reference point for regulation, right? So we take our output voltage and we scale it down by using some resistor network, right? A voltage divider network. And we compare that scaled down voltage to the reference. And depending on that reference or that error signal, we generate our PWM, right? Right. If we're too low, maybe we need to increase the duty cycle. But if we're too high, right, we decrease the duty cycle and so on and so forth. In this case, they've represented the reference voltage tolerance as a range of values, right? So for this 100 milliamp case, with this, I guess this is an H grade perhaps, we've got from 0.77 all the way up to 0.794, where our nominal value stays at 0.782, right? So this is typically what you would design for, right? This nominal value, but you need to keep in mind that the reference voltage does drift around, right? It has a tolerance band as well. And so your output voltage won't be perfectly regulated, right? There will likely be some error just due to this reference voltage tolerance along with tolerances of your different components like resistors and so on and so forth. But right, you just need to get a design that's good enough, right? So this reference voltage is something to keep in mind. Next up, we have line regulation. So line regulation describes a response to the input voltage. The input voltage is sometimes called the line voltage, or we're tapping off the line to, create some kind of regulated voltage for the load. And so this line regulation is defined by this delta VO divided by delta VI. Right? It's this ratio of the change of the output to the change in the input. And so this is typically specified in some kind of percent per volt. And in this case, for the LT8609A, we've got a typical value of 0.004% per volt. So if my input voltage changes by 1 volt all of a sudden, then you can expect the output voltage to change by about 0.004%. Right, so that's a pretty small amount, but it's just something that you should always keep in mind. Just like line regulation, we're looking at load regulation as well. So load regulation is another type of response, but instead of to the line voltage, it's actually to the load current. Right, so we're creating this regulated output voltage that is presumably supplying power to some downstream devices, and those downstream devices are going to basically absorb some current. So we always want to keep in mind how much that output voltage is going to change due to changes in the output current. And here you can see it's the output voltage won't change all that much, right? It's changing about 0.2% at worst, in the worst case here, right? If we suddenly change our output current to 3 amps, right, we're only dropping about 0.25% the output voltage. And now we have the oscillator frequency. So again, this defines your switching frequency, and this is usually programmed with a timing resistor for switching converter ICs that have a timing change capability. Some of them are actually fixed, but here in this LT8609A, we're actually able to program the switching frequency just with a resistor. And so the data sheet, these electrical characteristics specify, a range of different frequencies based on a fixed timing resistor. But usually you'll also see this in a plot. Right, if we look at frequency, there's usually some kind of plot that's based on the resistance. So if we sift through here, there might actually not be, but they do have, I guess instead of a plot, they do have a table here where you can kind of choose, you can see the progression of the switching frequency based on this resistance. And you could pretty easily plot that if you wanted to, or just use one of the values that they've specified here. But anyways, we can move on from that. Next up, we have MOSFETs. So again, inside of this integrated circuit are a couple of MOSFETs, right? We have our high side MOSFET and then our low side MOSFET, right? This one's referenced to ground. And these MOSFETs have some sort of resistance when they are conducting, right? From the from the drain to the source, there's some amount of resistance. This resistance will lead to conduction loss because we have some kind of resistance and current, so that leads to power, right? And here you can see that our top NMOS, right? This is an N-channel MOSFET, has 185 milliohms of resistance, and then it also has a current limit of, typically 4.5 amps. And if you were to go and calculate how much power that is, right, if we take our P is I times V, so then it's also I squared times R. So if I have 4.5 squared times my resistance, then I'm left with 3.75 watts, give or take. And so that's the most amount of power that they can continuously dissipate. Likewise, the bottom NMOS has some sort of resistance, right? This on resistance, which is a little bit less actually. So I would think that the bottom MOSFET can actually conduct more current. So let's actually, I didn't actually take that from the characteristics here, but we can check really quick. Okay, so I didn't take it because it's not there. Presumably you've got the same current flowing in the top and bottom MOSFETs there. So moving on. So efficiency is another electrical parameter that you'll see across a lot of data sheets, especially for these switching regulators. In this case, it's displayed graphically and as a percentage at a specific case, right? Here in the features, they specify over 93% efficiency at 1 amp, and then 5 volts out from 12 volts in. And then later on in the data sheet, they actually have this plot where they show different load cases and then what the efficiency looks like at all of those different cases there. One thing that's kind of interesting is that technically there is no efficiency at 0 load. Right, if you look at P out over P in, right, this is my equation for efficiency, how much of the output power is, how much of the input power is getting to the output. And if my output power is 0, well, then it doesn't matter what my input power is, right? It's always going to be some finite number, just, maybe it's like a tenth of a watt. But even at a tenth of a watt, this is going to be 0 efficiency, right? No power is getting to the output. So it's kind of interesting that when the output current is 0, they have some pretty high efficiency. So I'd be skeptical about that, but maybe they just are assuming like really, really tiny loads or something there. But anyways, so yeah, that's how the efficiency is usually shown in data sheets there. So next up, we have enable signals, and so these are used for remote control, right? We can actually turn on and off the integrated circuit just with some logic level signals, right? Maybe we're showing a little 5-volt signal out of a microcontroller to turn our switching regulator on and off. In this case, they tell you a threshold at which point our converter is enabled. And here in this LT8609, we've got a 1.05-volt threshold, and we have some amount of hysteresis. So this hysteresis allows our IC to stay enabled for some amount of time or some amount of voltage below our rising threshold. So in this case, the chip has 50 millivolts of hysteresis, which means that it will actually disable at 1 volt, right? So if we're already in an enabled state, it's going to stay enabled so long as that enable voltage is above 1 volt. And so once it drops below 1 volt, then we are now in a disabled state. And so that's kind of this remote control capability as well as hysteresis. And I think last up, we've got our output voltage ripple. So this describes the voltage switching noise. So as a reminder, we have two MOSFETs and we're switching these up and down. So this is actually going to not generate perfect DC, right? We've got a switching node here, which is going from whatever our input voltage is, right? So it's going from VN to 0. And we're then using some kind of LC filter to only pass through low frequency portions of this, right? We're getting rid of these high frequency transitions. And because of this action, there's going to be, right, this is not going to be perfect DC at the output. And in fact, it's going to have some sort of switching ripple due to this switching frequency and its harmonics, right? Because our filter is not perfect. And they will often describe this output ripple as a peak-to-peak voltage. In this case, they specify less than 10 millivolts peak-to-peak, which is achievable. And again, that really just depends on the size of your filter. So that, you need to pick out your LC filter components appropriately in order to actually achieve this output ripple that they've specified, right? It's not just going to come out magically at this 10 millivolts peak to peak. All right, so that's all I wanted to talk about there. Now we can get into this solar powered Arduino project. And I think I'm actually going to stop this recording and make a separate video for this, as well as for the flyback converter project, just so that I can try to keep everything nice and organized here. But thanks for tuning in. I'll see you guys next week.